All right, now we want to resume on introduction to deep learning. Introduction to deep learning. That's what we want to talk about. In the previous section, we've been talking about supervised machine learning algorithms, and their mathematical intuitions, their applications, and how to write your own algorithms. Now, today, on Thursday, I want to introduce deep learning. Okay, and that means we talk about what are neural networks fundamentals, what is perceptron model, what's the activation functions like the ReLU, the sigmoid, all those to become clear at the end of the day. We want to understand what is model overfitting and underfitting. I've been mentioning this all over in the past few days uh, on model underfitting and overfitting, and that's what we want to talk about. Next, we'll talk about the introduction to TensorFlow and Keras. Those are additional layers of libraries. Okay, on top of scikit-learn, we'll talk about other additional libraries: TensorFlow, Keras, and possibly PyTorch, which is not here. We'll talk about as well. So you'll find that we've been working with a lot of texts. Now, with deep learning, you can go ahead and work with even images and the videos themselves. So we find out like right now, Gemini is able to generate an image, while ChatGPT can generate a text. That means machine learning itself can go beyond just the normal text and can work with other files format like videos, images, uh, audios, all those. So all this forms the basic of NLP, natural language processing. Also, that's what we want to talk about in this particular session. Now, at the end of the day, we should understand how deep learning models operate and are implemented in Python. And we want to combine practical sessions that involves building a simple neural network. We want to train our basic model and want to evaluate neural network performance, like what we've been doing with other previous algorithms. We've been evaluating the performance of supervised machine learning algorithms and the unsupervised machine learning algorithms. And what we did yesterday on the last algorithm that we did on k-means, we used what's called silhouette score to check on the evaluation or the score or the performance of that k-means algorithm. Now, based on what you have here, I want to start right away on what is neural network. Now, by the way, deep learning, the basic fundamentals of deep learning algorithm is talking about neural networks. Very interesting concept over here. And just directly in my screen, if you can see it over there, I'm having a diagram. Okay. Before I move to the diagram, by definition, a neural network is the fundamentals for deep learning algorithm. So a neural network is a machine learning model inspired by the human brain, the neurons, the word neurons. So this algorithms has been inspired by the human brain. Take of the worst case scenarios like complex analysis involve human beings, like identifying images, like differentiating an image of a cat and a dog. That complex task is very simple for human being. You can define this a cat and a dog. Why? We've been training over some period, some time, and your parent has told you, see, if you see this particular animal with fair, short ears, okay, short, small, this is a cat. But if you see a huge one with long ears, black eyes, this is a dog. That's why deep learning itself has been inspired by the human brain, how human brain performs. Now, neural networks learns pattern by passing data through layers of connected nodes called neurons, like the human brain. Now, us as human being, we are able to generate or create machine learning algorithms that can the human brain. The same way how human brain is connected using neurons, dendrites, the axon, the nucleus, all that, we are also able to train our machines using connected nodes or connected points called neurons. So each neurons contain an information. I want to see how those informations are defined. Now, each of these neurons receive inputs. Okay, this can be like an image, raw image, applies some mathematical transformation, then passes that data to the next layer. Now we have layers and layers and layers that you can define on your machine learning algorithm. That's neural network. So we have a number of algorithms under deep learning. Like you want to talk about CNN, RNN. Now CNN, I myself I have normally CNN. You call it it's basically non-convolutional neural networks. You want to understand that, and RNN, that's recurrent neural networks. So they work separately at different contexts. Most images work with CNN, convolutional neural networks. And the good thing or the beauty of this is that the process, the cycle of training that particular deep learning algorithm is still the same. Later on, we'll see what are the layers, like what's the dense layer, okay, the output layer, the input layers, all that will be very clear. Now, each of these particular neurons or nodes applies some mathematical transformation. So these mathematical transformations are based on the algorithm that you want to choose. Okay? And after that, it passes that after that transformation, it passes next the result to the next layer. And those layers are also having the neurons again. Now, if you're allergic to math, you have to do math right now. You have to see how it works. The good thing all this has been abstracted in real life, we won't be writing the actual mathematics, we'll just be importing algorithms and libraries and train your neural network. Now, let me show you a diagram here and explain to you the relationship between machine learning neural network and the human brain. You've been asking yourself, how is if I tell like Gemini, generate for me an image of a cat sitting on a table. It's able to generate that. Where does where did it get this particular information? And how is it able to differentiate? Like if you tell it, generate for me a horse and a horse, generate for me a donkey versus a zebra. It's able to do that very clearly, perfectly fine. How? Its concept is just inspired by the human brain. And based on how you train your data, the accuracy of your output depends on a lot of parameters that we want to see in the next few days. Now, A is the human brain. Okay, the first node is the dendrite. Then you have the cell body, the nucleus. You have the axon that passes the information to the next, okay, neuron here. The same neuron has all the dendrite, the cell body, the axon, and the nucleus. So you have the axon terminal that relays that information. So think of it that particular aspect. Now, in machine learning, in deep learning, okay, remember deep learning is under machine learning, the subset of machine learning. Now, in deep learning, we are going to have what's called the input. So all this is going to be mapped into a mathematical transformation or a mathematical formula. By the end of the day, you realize computers only understand maths better, numbers. So all these are going to be mapped into a mathematical function or mathematical formula, like an image. All that will be transformed into mathematical functions and numbers, okay, which sometimes called binaries, being transformed back into binaries. Now, with me here, part B here, I'm having what's called the input. Okay, just take a close look of this. I'm having input from xn all the way to x2. Okay, x. Okay, I can call it x1 all the way to xn. in that increasing manner. So xn means any number of input layer. Now let me tell you how it goes. I'm going to take any input, I'm going to map it with the weight, which can be any mathematical value, the same from W1 to Wn. So I'm going to map each and every input to a weight n. All these weight are thus any values you can define. And then I'm going to take the summation. That's my first output. Then I'm going to pass that to the next layer. Now, with me here, I'm having x1, x2, x3, x4, x5, all the way to xn, maybe x100, 100. Now, in layman's language, I can take like, if I have a cat, okay, let me give a very silly example. If I have a cat, I can say the I to be having a value 1, okay, in the computer. The short ears be a value 2. That's just example. The long tail be a value 3. Now, I can also decide to say that let me take the I to be a value A. The I, the cat's I, can say A. Well, that for a dog, I can say maybe X. So let me take for the I, for the cat's I, I'm giving it a value A, modifying that. And for the ears, I'm going to give a value B. For the long tail, I'm going to give a value C. Then each and every input there, I'm going to multiply with the weight. A weight can be any value, like 1, 2, 3, 4, 5, 6, etc. So think of it like A1, okay, plus B2 plus C3. Now I'm going to sum all that. That's what I'm having here. All the weight, like x1 times w1 plus x2 plus times w2 plus x3 times w3 all the way to the last value. So I'm having summation here all the way from n, okay, 1 to n, of weight times the input values like w1, x1. I'm able to define my particular feature from that image. Then plus b, we have what's called the bias. We have what's called the bias. We have a b there plus b. Bias is any error. There's that chances for error or any bias. You have to add that. Okay. So that will form my first output. Let me pick some color. 1 minute. Okay, let's proceed. Uh-huh. I was going to show you basically how machine learning layers are defined. This is not the mathematical condition behind how you have having inputs against the weights to give you what is called the first output. So this particular output, all right, together with it, we want to have any activation function. Now we have four common activation functions, right? But the two most common, like ReLU and sigmoid curve. Those sigmoid curve we discussed earlier on when we talked about the logistic regression. You know how the mathematics behind the sigmoid curve there. We have what's called a ReLU. We also have others like the sine and the tan. Now, the most common ones is the ReLU and the sigmoid. So all that will be defined on the type of data you're working with. Okay. Now, you don't have to cram what's here. Don't worry about what's there. That mathematics. Don't worry about it. This is how it operates. Input times the weight which you can define, okay. Then we want to have a activation function, all right. This will give you the first output here. So you see what's here, what's there already. Output. Now this output will be passed as an input in the next layer. Now down here I'm having another thing. I'm having the input layer, hidden layer, and then the output layer. All right. If you can see my diagram, can you give me a thumbs up, Mr. Dennis? If you can see my diagram clearly on your side. All right, can you see the diagram right over there? Okay, now we have the input layer times the weight. Okay, that will form your first hidden layer. So you have hidden layer 1, 2, 3, all the way to layer n. Okay, minus 1. Now, the first layer here we are having W1, okay, times J. That will be multiplying the second layer, hidden layer, from the input layer. You're having the first output that forms the first hidden layer, and there's that particular cross multiplication all across, and that will be passed now to the next layer, up to the last one where you'll be having your output layer. Now that's how machine learning, deep learning algorithms are defined. Okay, is there any question at that point, Mr. Dennis? All right, if there's no question, now we have that particular mathematical intuition behind how the neuron operates. Like for a single neuron, we're having two operations that happen. Okay, so we have the linear combinations against the nonlinear activation. Now, neural networks are powerful because they can learn nonlinear relationship in data, something that simple models like linear regression, logistic regression cannot do. It's able to learn patterns of totally unrelated data, like nonlinear relationship. You don't have any uniform relationship on the features. Like, you see, learning through different kind of people. Okay, like I'm able to learn, like my algorithm is able to learn from people. Like I want to define this a human being against a dog. The first person is short, a human being. The second person is taller. That's also a human being. Okay, then I'm able to differentiate this with an animal like a dog. So there's that nonlinear relationship in my data. So deep learning algorithms are able to learn that from the data. How? You have the z function there is equal to wt, that's the weight, times the input plus the bias that I talked about earlier on, b. So b here is the bias that you add together with your input against the weight. So this a linear combination. What about the nonlinear activation? We have alpha is equal to alpha into z in bracket. So we want to multiply everything here in the nonlinear together with the alpha outside here. So I'm having a table here that defines what these parameters are. So x here is what's called the input vector, like your features. For example, if we're talking about human being, the height, okay, tone, the race. No, not yes, not that much. You want something that's direct. You can talk about the height, the weight, mm, the skin tone, the gender, all that. So X here, like what I'm having here as the input, can be the features. I'm going to multiply this with the weight vector. Okay, you understand what a vector is? So I'm going to multiply this particular input with a weight vector. Like what are the learned importance from that data? You can define that using a vector. A vector is like known as an array, kinda. So each input, I'm going to multiply with an array vector. I'm going to add the bias together with the activation function. All these things will be clear at the end of the day. You're able to do that practically. You want to add those activation functions and generate the layers. Now, bias is the offset of the errors that you have to include that together. And the activation function that we normally use is the ReLU and sigmoid. Okay. All this will give me the output. Output A here. So the alpha times the what I have here is the linear combination. Now this is structure of a feed forward neural network where they feed forward and feed backward. So this is the structure, basically what I've shown you here. Okay, input layer, hidden layer, and the output layer. I want to understand how these particular things work. So if we start writing the algorithm, you know how it operates. Now, input layer is the raw data, like the features. Hidden layers are the patterns. Okay. Then you have the output layer is the possible prediction out of the multiplication of the input against the weight plus the bias. This will give me the output layer, the prediction. If I was talking about human being, I'm going to say, oh, this is a human being. If I was talking about a cat, I can say, oh, this is a cat. How? By matching what I'm having in my hidden layer. I'm going to combine that, like what I'm having here in this diagram. Everything from the hidden layer is multiplied with the first out, like see L, this particular node here, that multiplied with the y1 with the y2 here, the same there, the same here, up to the last one. So every input, I mean every feature that's originated from this particular node in the hidden layer, I've multiplied that, all of them, to generate my first prediction. Maybe this is now a human being, okay? Then y1 can be like a cat, if you want to do that prediction. Same way, think of it like disease predictions. How am I able to say that's now cancer, why this not pneumonia? By checking on all those particular things using the deep learning itself. Like our patients, I mean doctors, able to differentiate images from, okay, those X-ray images, are we able to with this particular type of cancer and at what level? All those are the concept of deep learning. All right. That being said, now in my hidden layer, what I've just said, in my input layer, this receives the raw features, e.g., the reading score, temperature, writing score, all that. The hidden layer is that each neuron applies that particular mathematical function. Z, okay, is equal to W against X. W is the weight, super, okay, T there is anything like maybe 1, 2, 3, 4 up to the last, plus the bias function. So the bias, you have to include that too as an offset. Then for me to work with nonlinear, I'm going to pass what I'm having here, okay, with an alpha, anything. I hope that's clear at that point. Now, output layer produces the final prediction, like a number of for regression, a probability for classification that will be defined in the output. Now, what are the common uses of deep learning? Image recognition. This thing cannot be done by simple linear regression. No, you can't do an image recognition. That one requires a deep learning algorithm. Like we have common ones called the YOLO for object detection. YOLO. Now, another use case is the time series prediction, like RNN and LSTMS. Okay, so we see all these components form under the deep learning algorithm. So, like CNN is there, RN is there, LSTMS is there. These things will come perfectly fine and clear by the end of the day when you start the actual implementation. Another thing is the language translation, like transformers. Okay, what you normally use the ChatGPT, the DeepSeek, all those particular mm, transformers that can assist in learning language translation. Like if I just take a text, give to ChatGPT, I tell it, "Hey, translate this to me to Chinese." It's able to generate for you an output. Disease detection, like classification networks, like CNN is a good example. Okay, for you to come up with a disease detection. I'm able to classify disease based on their symptoms. So think of symptoms like the input layers, okay, all the raw features in that particular disease. Like game playing, this now under reinforcement learning. I'm able to play chess in my mobile phone. I'm able to play pool table, call it billboards in my mobile phone against a computer. So that's under reinforcement learning. So that's it for the basic introduction against deep learning. So I'm going to start working up with the deep learning algorithms by specifying the algorithms. Okay, so in my new sheet, I want to come up with a new sheet here. drive. We want to see which are the possible libraries that you have to import for you to come up with a deep learning algorithm. Now, I'm going to share with you all those notes that I've just discussed with you, plus the diagrams and the mathematical explanation on how it works. So that's how the basic understanding on how deep learning neurons operate as inspired by the human brain. Okay, the neurons, the weights, the inputs, the hidden layer, and the output. Now, I want to start writing a machine learning algorithm. We're still going to work with the student performance data set, which will load later. I want to show you what are the algorithms that you have to import or work with when you're working with deep learning algorithm. So let's import all the necessary libraries. Okay. So because we want to work with our data, the first thing is you want to import pandas as PD. Okay. The next library you have to import is the NumPy. Import NumPy as NP. For visualization, we want to import the obvious tool. Just import matplotlib dot pyplot, okay, as PLT. The next one is going to import Seaborn as SNS. Okay. Now, let's now import the deep learning library. Our first one, let's call this deep learning. Come on. All right. Just follow up what I'm doing. So the first one, I'm going to import the TensorFlow itself. So I'm going to say import TensorFlow. TensorFlow. Okay. Correct. Check the spelling as TF. Good. So this is our machine learning library. Yeah. So this is our machine learning library. Import TensorFlow as TF. So think of TensorFlow as the scikit-learn, as the NumPy, as the pandas, all that. So this is a machine learning library that helps you to work with deep learning algorithm. So we have others like Keras and PyTorch. Mostly they work in hand. Okay. I'm going to show you this particular line of code, understand it well, to for us to save the time for us to do it together. Now let's import. We want to split our data. We want to split our data, of course. In machine learning, you have to split our data. So we're also going to do what's called model evaluation. We're also going to do data preprocessing. Okay. So that what does that mean? I'm going to import the trend split. Okay, the standard scaler for preprocessing, and I'm also going to do evaluation. Now, for us, we want to use what's called the mean squared error (MSE) for doing machine learning. I mean deep learning algorithms evaluation. So let's import the three. So okay, so I'm going to say import. Okay, So let me say from sklearn dot, okay, model selection. Model selection. I want to import the train test split. Okay, so this particular library helps in um, data splitting into training and okay, and the validation sets. Again, from sklearn dot what to do what's called the standardization preprocessing. So from preprocessing preprocessing from sklearn preprocessing import standard scalar. Okay, so this should be lowercase. Yep. So we have the standard scalar. Of course, you know why we use standard scalar discussed earlier on. Again, from sklearn, okay, dot matrix, we want to import one more library for evaluation, mean squared error. Okay, so this basically is called MSA. We also have an alternative one, okay, called MAPE, mean average percentage error. Okay, that's now the percentage of the average of the mean squared error. These are also related to what's called residuals. Residuals. So you're going to find out what residuals are. Uh, Residuals, you can relate this to errors. Uh, Now let me see if this is okay by say print uh, all libraries. I'm just going to check if everything is imported successfully. Successfully. Okay. All right, let's connect. We never connected that earlier on. Let's connect. Meanwhile, do you have any question based on what you've done in under importing libraries, Mr. Dennis? Okay. The good thing I'm explaining while I'm doing so, yeah, of course, you just have to match. Now let's move to the next thing. Now, in machine learning, we are going to work with some very funny ideas. Like, suppose you're working with the Jupyter notebook, okay? First, you're working with Google Colab. Suppose you want to work with Jupyter notebook, even in Google Colab, I mean, we are going to use our computer resources. Actually, compare in simple terms. Now, if I'm working with images, images are basically in form of pixels. Where are we going to get the pixel from? From our machines. And each pixel has its own binary annotations. Okay? Now, that means you have to work directly with our machine. Direct to our machine. So I'm going to import one more library. I'm going to import one more library commonly used. So I'm going to import the entire my machine. Okay, it's simple as my machine. I'm going to import OS. Import OS. So I'm going to import my entire computer. So I'm able to work with my entire computer directly. So computer is basically I mean the operating system. So this OS will enable me to do any manipulation with images, videos, all that directly from my machine, because that's where I'm going to get the pixels transformation or the mapping of my pixels if I'm working with images itself. Now, so we want to suppress TensorFlow information errors. Okay, there's one particular thing I'm going to do, though you can do it later. It's just perfectly fine. It's still okay. So I want to suppress when you're working with the TensorFlow, there's no particular errors or communication to be showing you. I want to do what's called suppressing. I want to suppress the TF. errors or error messages. You'll see them. I'll show you one there and I'll remind you. When we're here, I'll remind you. These are the one of the TF errors that we're going to find out. Now, we're going to say os dot environment environ. Okay. For my OS environment, I want to suppress this error. So you have what's called the TFCPP minimum log level. Like I'm going to define my log level. I'm going to say, okay, let's say TF underscore CPP underscore minimum of my logs. So I'm log define my log level here, and then I'm going to give you some any value. For me, I can say it's like 2. Can I give it 1, 3, or 2? Let me just use 2. Again, this should be full bracket. Okay. So what have I done? For my OS, I want to suppress any error message coming from the TensorFlow. Though if I leave it to cluster down here, but I want to suppress them though so that they don't show up. I only focus with what I want. So TensorFlow CPP mean log level defined into 2. Okay, we'll check that later. So I can check the version of TensorFlow that I'm using. Let me run that. Let me check version. It's a good thing to understand the version that you're using. Now, TensorFlow versions. I'm going to say TF, what I've imported here, TF dot version underscore version, okay, then underscore. Now let me run this and see the version I'm having. I'm using TensorFlow version 2.20. Maybe you have version 1, version 3, version 1, 2, 3. So I'm getting the latest version, TensorFlow 2.20. So if I'm working with, let me tell you how it goes. At some particular point, there are some libraries that are coherent or matches a given version of or TensorFlow versions or libraries. Which example can I give you? Ooh. At some point when you're working with let me give you a very silly one. You'll find that maybe sometime we're not using .pyplot. Okay, we're using for import matplotlib as PLT. That one maybe you used to work with earlier versions of Python. Now, if you use .pyplot, the version that you're using it, you have to understand. Okay, that's what basically I'm done here. So this is version 2.20. No problem with that. You can also downgrade, upgrade on the version that you want. Now, let me copy this cell and give you, since that you understand it, let me give this code. But every time, try to write these particular things yourself. Okay. Right now, what's defining us is the time. So at every time, try to write these things that are quite long. If try writing it together, it will take twice amount of time, and that one will the consequence. So just copy that and run and see if you're having what I'm having on your side. Sorry. If you've managed to run that can sorry, if you've managed to run that code, you can give me a thumbs up kindly, Mr. Dennis, so you can proceed. Okay, that's great. Okay, if there's no question on that and you've run it, you have it. There's no need of you writing it one by one because of time. That's okay. Let's go that way. Now I want us to load. Okay, I want to load two data sets. The first one I shared with you. We want to okay. We want to work with two data sets. I mean, the first I sent you earlier on is for students' performance. We also want to work with the bikes data set. Okay, or the sole bike data set. So the same way, we're going to load our data to our work environment, and that one is very obvious. You know how to do that. Now we want to use two data sets to throughout this particular notebook for deep learning. We want to work with the student's performance data set to help us predict math score from reading and writing score. Okay, and we're also going to work with uh, bike sharing dataset that will help us. We're going to write deep learning algorithms that will enable us to predict bike rentals from weather features. Okay, like if it's raining, should the prices increase or not? Uh, if there's too much, if it's sunny, like if it's too much, okay. If the temperature is high, should we? What will determine the renting rate? Okay, so that's essentially what we want to do. We want to work with the students' performance together with the bike uh, sharing data sets. So let me see how I can show you those particular things. But I believe I shared those particular data sets there too. So let me load them here. I showed you via email the students' performance and the bike.
Hello, poa. Nauliza nani yuko hapo ndani kwa?
So let me load my data sets, the two of them.
Hello. Hello. Hi. Alichukua maji. Mm. Hadi sijui. I think nilifungua dirisha. Ah. ndani ya bedroom yako utakuja.
Yes, can you hear me? Okay, let me share with you. Let me give you a notebook here with the link. So click on that notebook. There's where I've placed the URL for that dataset in my Google Drive. You just download it. Hope you can see that in the chat section. Okay. Now let me change that to something else. Anyone with the link. Uh, anyone with the link. No. You can retry that. Okay, I think you have access through the second one. Click the second drive to see the cell bike sharing data set. Hope you're able to do that. Oh, same data set. All right, all right, okay. But that's in performance. I'll change that later. Okay, I think I'll share this thing. Okay, let me do this. Can you access your email right now? I share with you directly by your email right now. So let me do so. Okay, I hope you're able to see the data set in your email. The soul. The soul bike sharing. Okay. It was really loading. I don't know why. Loading. It was really loading on my side. It has taken time. Okay, as it downloads, let me read the student's performance CSV data sets. Although we know how to do this, so let me quickly read the student's performance data set. Amongst the students is equal to pandas pd dot read CSV. So we are working CSV file there. Then said I'm going to pass my file directory. Copy path. I'm going to say students dot head. Okay, okay, there's something missing here. There should not be brackets. So for that. So I'm having my data set there for students of gender, race, parental level of education, lunch, test preparation cost, math score, reading score, writing score. So those are the variables or the columns that I'm having in my data. Okay. You can even always try to embed this using a try and catch error. We'll show that later. Okay. Now let me try to read the bikes dataset. So the same approach. I'm going to say bikes is equal to pd dot read csv. Okay. Inside I'm going to pass my file path. Cell bike path. So let me see what I have. The first five columns, I mean the first five rows that I'm having. I'm going to say dot head. Bikes dot head will show me the first five records overview of my data. So this is what I'm having for my bike. The date for renting, the rented bike, the number of bikes that were rented that particular date. Okay, hours or it was rented like zero, like 00 clock. The temperature when the bike was being rented, the humidity when that bike was being rented, the wind speed, the visibility, the dew point, the solar radiation, the rainfall. So all these are the features. Okay, so you still have some more here, like snowfall season, whether it's a holiday or not, whether it's a functional day or not. Okay, all these are the particular features that will enable us right there deep learning algorithm to determine the number of bikes that were being sold on that particular day. No, being rented on that particular day. Yeah. So I hope that's done. Now, what's our next thing? Our next thing is to talk about the perceptron model. Okay, like we want to build a simple perceptron model or neural network based on our two data sets. Like out of my student performance, I want to work with for some features, reading score and writing score. So let's understand what the perceptron model. For that, we have a target of y, that's the math score, and we want us to discuss about the perceptron model. Okay, and I think we can end it for today at that point, right? Now you've seen what's the neural network, what are the neurons, what's the weight, input, the activation functions. You understand that. So our next thing here is talking about the perceptron model. So you want to work with this particular data set to understand the perceptron model. So now I want to show you something. I want to show you something before we start the implementation behind the perceptron model. That's the simplest way, the simplest neural network. If you're in biology or in health, you know how the brain perceptron or the neurons occur or operate, or how are the signals being transmitted from all the way to the dendrite to the axon to the next terminal or the axon terminal. Now, perceptron model is the building block of all neural networks. It's the building blocks of all neural networks. Okay? The same way, neurons is the building block of all the deep learning. The deep learning algorithms work based on neurons, inspired by the human brain, neurons. Now, perceptron is the building block of all neural networks. So it does particular things. It doesn't have hidden layers, just have a simple direct input and output layers. So remember the diagram behind uh, the neural network itself, where the input layer, the hidden layer, and the output layer. So the simplest model without considering the hidden layers is what that now we call the perceptron, or the simplest neural network. It's the basic, so that it has to be very simple as it is. It doesn't have any activation function. So what basically it performs? Basically performs a pure linear transformation, no activation function. Okay, you don't have something like the sigmoid or the ReLU activation functions. Now, this makes it mathematically identical to linear regression. Okay, so understanding the perceptual help us to see exactly what we gain when we add hidden layers and activation functions. We want to build on this by adding a hidden layer and activation functions. So, because for us to come up with a perfect output layer, we should remember two things. You have to have the hidden layer plus the activation function that's going to come with, like ReLU, sigmoid, tan, sin, all that. For us, we want to use mostly ReLU and the sigmoid function. Now, I want to do something similar to linear regression, okay, but using a neural network. Now, in my student performance data set, I want to target some particular features, reading score and writing score. So, in simple terms, quote unquote, I'm going to do a linear regression between the two features, reading score and the writing score. But I'm not going to do this direct. The difference while working with the linear regression against working with the neural network, which one works well? We'll see that at the end of the day. Now, my target here is the checking on the math score, my target variable. Yeah. So that's what we want to see in the next session. I want to understand the perceptron model using that particular example for students' performance. Now, you can check with me if you have successfully imported the two data sets, and that's where we shall proceed with tomorrow. Okay, by understanding the perceptron model or the simplest neural network. Now, back to you. Have you managed to download and read the two data sets with you? That's good. Now, by the way, okay, what you're doing is now on the high level. So you are now in the advanced concepts. Now, let's just give you what's there. Let me tell you the truth. We're in the advanced concept. What is going to be discussed here, it won't be perfectly clear directly like those ones in the basics. So in one particular point, I'll be coming mention something that I've never discussed earlier on. So you can note it down, okay? Or when you're watching that video, you note that particular concept down, and you can go ahead and do some research on it later. Like if I talk about a ReLU, what's a ReLU activation function? You can learn about a ReLU and the mathematical into how ReLU work. Because sigmoid, you know how it works. You know how a sigmoid function work because we discussed that earlier on. Now, you'll be asking yourself, what about ReLU? You'll be able to do that. The only problem is that time won't allow us. I myself was wishing to tell you all those particular details one by one, but for what I'm seeing here, we still have some. Yeah, we're playing around with time for us to cover everything as required. I'm giving you, for me, for it appears like something like basic. Though I'm not going to go in the basic way. I'm going to talk about in more advanced level. Back to you as a task or assignment. Go and do your research on everything I mentioned and hasn't been clear from the word go. Add additional layer of effort, research on Google what it meant, uh, in addition to what I'm telling. But I've been trying to exhaust all those concepts right over here. Now, nothing complex. We are in the advanced level. Don't worry about anything. That's how it goes. Now, let's stop for today at this particular point. Tomorrow, we want to understand the perceptron model by doing a linear regression in terms of neural networks. And then we want to do a simple linear regression in a normal way by importing the linear regression algorithm. We want to compare the two by checking at the matrices or the evaluation, the output, which one works best. And you'll see that it's obvious neural network works well or it performs simple linear regression. So that's it what we have for today. Just have to stop that up this point. See you tomorrow. Tomorrow's on Friday. Should see you tomorrow. But more details we'll do in the next week to the capstone project. So less than that for today. See you tomorrow. Unless there's some pending or burning questions based on what I've discussed, I'll be able to clear that right over here. What? Yes. You've seen some mathematical explanation. I know, I know. Oh, you did them, you mentioned them in the campus by then. Mm. By the way, like, what the, like there's something that was called Bayesian algorithm, naive bias. So I was wondering where should I use this? Like probability of A given B against probability of B given A over. Remember something of that sort? Eh, And exactly.